Hello class, I hope AP exams are going well. I'll try to keep this video as short as I can. This is the Unit 4.2 Notes, Section 5.3. I did the warm-up to save time. You'll notice that I use derivative notation for derivatives of each function. I also use a capital letter for all of the antiderivatives, and I added plus C to them. All right. So let's get started with our lesson on definite integrals and antiderivatives. The three things we're going to focus on today are properties of definite integrals, average value of a function, and how that relates to the mean value theorem of definite integrals. All right, there are pretty much three main topics here. I only expect you guys to be accountable for two of those major ones, so we'll focus on those today. As you can see, I already have a graph drawn here. I've tried this a couple times. So let's get into order of integration, and I'll explain what this graph is showing. So order of integration is one of the first things that we need to focus in on. Until now, you've had things that have gone in order from the lower limit to the upper. Unfortunately, our limits of integration are messed up here. So let's say B to A is actually from 4 to 1, and that's where my 1 to 4 is shown here. But if it's out of order, instead of actually creating area, you actually are going to be getting rid of area. So if we were going from 1 to 4, and my function was y equals 3, or f of x equals 3, so 3 dx, as you can see here, let me erase what I did earlier. You would see that we would be creating area from 1 to 4 under the curve and between the x-axis. You would say, you know what, the area then, in this case, is a width of 3 and a height of 3, not drawn to scale, so area is 9 units squared. The only issue is that that's going from 1 to 4 and not 4 to 1. If we go from 4 to 1, we're actually taking area away. So let's take a look here. We're going to be taking the area away instead. This is being erased. It's pretty simple. All we have to do is change our order of integration, call it from 1 to 4. That would result in throwing a negative out front. So instead of creating area, we take area away. And this becomes negative 9 units squared instead of 9 units squared. All right. So you always want to make sure your order of integration goes from the least to the greatest on a number line. That's how we create area. And sometimes we do have to switch that integral, and we would just throw a negative out front. If it's already negative, then it would become positive. All right, the second rule here is this one, and it's from A to A. Well, if we're going from the same number to the same number, let's say we were going from 4 to, let's say we're going from 4 to 4. Well, we are not going to have any thickness of an area here. Let's get rid of that. I'm going to move this here. Oops. Imagine if there was no distance whatsoever. So here you see from 4 to 4 of any function, we are going to have no actual area created. It's just nothing there. This right here, this right here has no thickness. So that always ends up being 0. I'm using numerical numbers here, but numerical integrals here, but they could all be different. So let me clean this up. All right. Let me bring that back. Okay, so let's take a look at this one right here. The constant multiple rule from a to b of k f of x dx. Well, that's just saying, let's say we have from 1 to 4 of the function 10. I'm going to use a constant function. It could be linear, quadratic, it doesn't matter. It could be 5x squared. What it allows us to do is actually factor it and take the factor out. So let's say I factor this into 2 times 5. I'm going to show you how these are equivalent. So let's say I factored out the 2 and I left the 5 on the inside, and it's still from 1 to 4. Let's see how these are equivalent. Let's take the graph that we have here, and we went from what, 1 to 4? We keep using the same example, 1 to 4. 1, 2, 4. Oops. We're going to do 1 to 4. And let's say, not drawn to scale, but this function now was 10. I'll change it so it matches. The function now is, oops. Function is 10. Okay, you would say that it has a thickness or a width of 3 and a height of 10, so the area of this one must be 30 units squared. Okay. That is our first one that I focused on, from 1 to 4. From 1 to 4 of the function 10. If I went from 1 to 4 of the function 5, you would just change this to a 5, not drawn to scale, remember, 5. We would then instead have an area, which is 3 times 5, which is 15 units squared. Those are different because we factored that 2 out right at the beginning. So we have to make sure that we include that 2, that's a product, right here before we are done, which would leave us with 30 units squared. So you see that if it was, 5x squared, you could factor the 5 out, find just the area of x squared if that was your function, and then after that you would multiply it by 5. The area will be the same regardless of if you find the antiderivative of 5x squared or the 5 times the integral of x squared, as long as the a and b are the same limits of integration. All right, next we have, I'm going to clean that up a little bit. We have the negative. I'm not going to spend too much time on this. That negative and that negative are the same. Just like if you were to integrate with a negative function, or you pull the negative out front and multiply it by the area of the function, you will end up with the same thing. If this was, for instance, 5x squared, negative 5x squared, we could pull the negative 5 out and leave it as x squared. Just multiply the negative 5 at the end once we find our area. Or we are able to say, well, no 5, we're going to leave the 5 inside. We could do that as well. That's legal. We just have to make sure we multiply it in at the end. Okay, the sum and difference rule, pretty simple. We just need to focus on a couple things here. Let's erase that. Okay. We need to focus in on A to B, which is repeated. This addition here is what we see here, or subtraction, right? The difference or the sum. And f of x dx is separated from g of x dx. So pretty much what this is saying is that if I had something that went from 1 to 5 of x plus 2. I could call my first function x and my second function 2. then I'd be able to separate them and find just the antiderivative of, the integral of x, and then just the integral of 2, as long as my bounds stay the same. So the area of them combined would be the area of them separated, as long as they have the same integral limits of integration. That differs from this next one. This next one, I need to have the same, the additive property. I need to have the same function. Oops, that's not what I wanted. Right here. The same function, f of x dx. If the same function exists, but I have different areas of integration, from a to b and b to c, think about this as a number line. B comes between a and c. So I'm actually allowed to just go from A to C of that same function. Here's what it would look like. I'm going to draw it out over here. Let's use some different colors. Let's call this our x-axis and our y-axis. Let's give it numbers. We'll call it 1 and 3 and 3 and 7. So that would be from 1 to 7. I'm going to use a constant function. I will call the function 4. Y equals 4. So here's y equals 4. I'll graph that one. Now, let's take a look at our 1 and our 7. 3 is a little bit closer to 1, not drawn to scale. The same function exists, y equals 4, in all of these cases. So let's look at the area from 1 to 3. This is the area from 1 to 3. And let's add to it the area from 3 to 7. As long as that function is the same, wouldn't we agree that that is actually the same as 1 to 7 collectively? Doesn't matter if it's linear, quadratic, cubic, it doesn't really matter. We are able to combine or separate anything. So if you are going from 1 to 7, you can break that down into 1 to 3 and 3 to 7. That is our sum and difference rule, right? It's just being broken apart. Or the additive rule allows us to put it back together. These are just inverses of each other. So the sum and the difference here, this one and this one, are inverses of one another. Okay? You can ignore for right now 6 and 7 because we're not going to talk about the domination of integrals or the max and min inequalities of integrals. I just want you to focus on the first 5. I feel like these are the most important. All right, I'm going to end the video here so that we don't get disconnected, and I will start a second video for the next part. All right, welcome back, class. I just want to separate them while we have what we have. But we're going to start with example 1. This is one of them that you're going to be accountable for on the exam. On the quiz, using the rules for definite integrals. So here we have 3 integrals. Each one of these are area. So in the first one, I don't know what my function is. I know where the function exists. It's between -1 and 1. The area here is 5. The area for the second one is -2, and the area for the third one is 7. That's awesome. They've done all the work for us. We don't need to see, nor do we necessarily care about what the function looks like. We just know that the area between the function and the x-axis between all of these locations are are 5, -2, and 7. You'll notice as well that we have some different functions. We have f of x dx as a function, f of x dx as a same function, and h of x dx as a function. You'll notice further, hopefully, that these go from -1 to 1 and from 1 to 4. So you will see that they could get extended from -1 all the way to 4. Let's take a look at the 6 examples we have. They're a little bit diverse, so I want to make sure we include all of them. I'm going to, up front, separate them so that they are, I'm going to separate them so that we have a little bit of room to work in and we're organized. Okay. The first one we have is 4 to 1 of my function. So I'm just going to use the substitution property. I want to substitute in 1 to 4, which I know has an area of -2. But I can't do that because I'm going from 4 to 1. So let me fix it so that I am going from 1 to 4. I'm going to rewrite 1 to 4, f of x dx. And the most important part here is that I throw my negative out front. Because I changed the order of integration, I'm not creating area, I'm taking area away from 1 to 4. Ironically, area is already being taken away from when I go from 1 to 4. What I do know is that from 1 to 4, there is more area below the x-axis than above it, which is why the result is negative. It's weird to say negative area, but it's just represented by if it's below the x-axis or if we read the graph from right to left. So wherever I see 1 to 4 f of x dx, I'm allowed to use -2, which is right here. So I have my negative, and I have -2. That negative is the one I placed out front, and the second negative is the one that's just coming from the function. That leaves me with 2. So let me erase this. Oh, I messed up. The area here is equal to 2. Pretty easy, right? Second one gets a little more complex. We are going from -1 to 4. That's the same as saying -1 to 1 and 1 to 4. Let me make it look that way so I can use the substitution property. Let me call this one, let me move it up a little bit. I'm going to call this, -1 to 1. I'm going to add to it from 1 to 4. I'm going to add the 2 areas that I know. And that, again, if we look up here, is our sum and difference property. I'm able to separate them. I apologize, it's my additive property. I'm going in the reverse order of my additive property. So now that I see this, I can substitute in for the -1 to 1, which has a value of 5. And I'm going to add to that the value -2, and we get a total value of 3. And that's it. It's easy when they give you all the information you need. This next one, I'm hoping you guys are getting a little bit better at this. We are going to do 2 steps in one. I'm going to, I'm going to break up the function by the plus sign. I am also going to use the 2, I'm going to throw the 2 and the 3 out front. So I'm going to break this down and separate and do everything all at once. Let's do -1 to 1. Oh, I apologize. I didn't do what I just said. Let's do 2, -1 to 1, f of x dx. I'm going to add to that 3, negative 1 to 1, h of x dx. So wherever I see negative 1 to 1 f of x dx, I'll put in the value 5. And then wherever I see negative 1 to 1, h of x dx, I'll put in the value 7. So I have 2 and 7. So 2 times 7 plus 3 times 5. I get, whoops, did I do that right? 2, I mixed up my 5 and 7. 2 and 5 and 3 and 7. I get 10 plus 21, which is 31. Very, very nice. All right, letter D. Letter D is interesting. We have 0 to 1 of f of x dx. You don't see it up there, right? I see negative 1 to 1, but I don't see 0 to 1. I can't just divide this in half. I can't just say, well, you know, the integral from negative 1 to 1 is 5, so it must be half of that because 0 to 1 is halfway between negative 1 to 1. We don't know what the function's doing or what it looks like, so we are just going to say that this is not applicable. I actually don't like saying not applicable. Let's see. I'm going to say not enough information. The book will say, you know, not applicable or not possible. It's possible to calculate if we had enough information. We just don't have enough information to do that. Let me show you, this is a side note, this does not have to do with the problem, but here's something you're allowed to do. You're actually allowed to think of a number line that goes from 0 to 2. And let's say we have some function, I don't know, I'm just going to sketch out a function. Let me make it constant so it's easier to view. Okay. If I were to have, for instance, the number 1 in here, I would have some area. You know what? Let me make it linear. Let me make it linear. That's my linear function, and I'm going to change. I'm going to erase this for right now. Let me clean this up. Okay. Let's say I had a linear function, and I had area here. You'll agree there's some type of area happening between 0 and 1, which I'm trying to just approximate here. And then let's say I also had some area that's happening from 1 to 2. Now, if I know the total area if I'm given 0 to 2, and I'm also blah, 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 and I'm also given 1 to 2, then I'm actually able to say that 0 to 2 minus 1 to 2 is equal to 0 to 1. Let's think about this. 0 to 2, this whole area. If I take away from that the 1 to 2 part, I take away that part, aren't I left with the 0 to 1 part? Which is this part right here. So think about a number line, and if it works, it works. If it doesn't, it doesn't. In this case, I had 1 to 4 and negative 1 to 1. Neither of those overlapped each other. Therefore, I can't do any type of addition or subtraction that would fix that. Just like above, if I were to have 1 to 3, 3 to 7 equals 1 to 7, if I were to, like, for instance, move this part over here, it would be 1, maybe not that. Maybe move it right there. It would be 1 to 7 minus 1 to 3, and that would be equal to 7 to 3. And you're just manipulating the additive property Don't think too crazy about it. Just think about it as if it was a number line. What legally would make sense? And what legally can you do? All right, here we have -2. We have -2 to 2 of h of x, and it looks like we have -1 to 1 hx. That's all we're given. Again, you can't just assume that, oh, well, -1 to 1 is 7, so I'm going to multiply it by 2, and I get -2 to 2. That's not an assumption you're able to make. Again, if this was a constant function, fine, but we don't know that it is. So we have to really make sure we know what we're doing, and we're not just making guesses that are not appropriate. So this one's pretty easy, not enough information. Whoops. We're just going to write not enough information for this one as well. I'm running out of colors. I'm trying to keep them separate so it's organized. Not enough info. Okay. The last one, -1 to 4 of both functions. Well, we win some, we lose some. That's a winner, and this one is a loser, because we can go from -1 to 4 of our first function, but not, right? -1 to 4 is okay. We can go -1 to 1, 1 to 4, but we can't go -1 to 4 here. So again, not enough information. Not enough information. Let me show you the most legal stuff we can do with this. We are going to break -1 to 4 f of x dx. And we'll add to that -1 to 4 h of x dx. Now, I don't see any of that up there, so let's break it down further so that it matches some of the information we were given. -1 to 1 f of x dx plus plus 1 to 4 f of x dx. That is fine. And then we have plus -1 to 1 h of x dx. That was when we were listed. And we don't have -1 to, oh, I messed that up again. Let's clean that up. We don't have 1 to 4 h of x dx. So we are good with that one, good with that one, good with that one, or not good with that one. All right, I'm going to save this again so that we do not lose where we are, and I will come back and show you example 2. All right, welcome back. We are going to go on to example 2. This one is not one I'm going to hold you accountable for. I just got to show you what it's really talking about. It just says show that the value of 0 to 1 of this function when we integrate is less than 3/2. We can do it two ways. The first one we can look at is a graphical method. I already put a graph of it here for you. So I'm just going to label it a little bit further. We're counting by 0.2. I'm sorry, that looks like -8, but it truly is 0.8, 0.6, 0.8, 1, 1.2, 1.4, 1.4, 1.6. Okay, so it goes up to about 1.4. And we're looking between 0 and 1. So let's assume, so we know that it's one width wide, it has a width of 1, and it goes up to about 1.4. If we overestimate, the easiest thing I know of would be to create a rectangle here for 1.4, So I'm making that rectangle now. Whoops, that's okay, you guys get the picture. This area is 1 times 1.4. So this area is, when it's all shaded in, this area in here is it's a square area of 1.4. So we would say area equals 1 wide times 1.4 high, which is my dog is going crazy. Hold on. All right, welcome back. I apologize about that. So area is 1.4 units squared. All right, so that was our approximately. So that proves as less than the 1.5 that we see here. So 1.4 is less, well, let's just put it right here, less than 1.5. All right, the only other way we could do is more algebraically. What we do know about the cosine function is that 0 to 1, regardless of what it is, right, cosine of 0 or cosine of 1, we know that it oscillates between -1 and 1. So I'm just going to sketch in here a cosine function. We're going to say, I'm just sketching in a random cosine function. That's a bad example, but we know it oscillates between 1 and -1. So we have when x is 0, which is right here, and when x is 1 is somewhere over here, but again, somewhere between 0 and 1. So let's just actually find the square root of 1 plus cosine of x at its maximum number, because we're trying to prove less than. So if we test the max, we will test the less than part of it. So we have cosine of 0 is 1, so we have 1 plus 1. So the square root of 2, square root of 2. We have the square root of 2 high, and we have 1 wide. So in this case, area at its max would be width times height. So area is approximately, the square root of 2 is actually, let me see on my calculator, it's 1.4. I have the square root of 2 is 1.414 units squared. So again, this proves it's less than the 1.5 units we were talking about, which is kind of what we see up here. So that must have been a little bit higher than 1.4 and then dropped off, which took some of that area out. All right, again, you're not accountable for this one, so I'm going to put, not accountable for this one. But it's just nice to know and nice to see. Okay. Section 5.3, here we go, average and mean value. So we're going to talk about the mean value theorem. I'm going to save this video and start a new one for the mean value theorem. All right, so mean value theorem. The mean value theorem seems, might look a little bit more complicated than what it truly is. So if I wanted to find the mean or average value of your tests, I would just add up all the tests and divide by the number of tests that there are. Same thing goes for the mean value theorem. We are looking for the total area and dividing it by the beginning and end of its interval. So if there was a total area of 100, but the function was, let's say, linear, and it was going from 0 to 10, then on average, each unit has 10 square units. So Let's make up an example here. I'm just going to throw in, let's see, let's go from 2, let's go from 2 to 8. So, oops, 2 to 8. So if this goes from 2 to 8, and this particular function between 2 and 8 has has 36 square units. What I'm going to do is I'm going to write 1 over 8 minus 2. That's going to give me my width, which is 6. I'm going to multiply that by the integral from 2 to 8 of f of x dx. So I'll have 1/6 times 36, which is 36/6, which is 6. What this means is that total area is 36. The interval in question is 6 units wide, so its average would be 6 units squared. All right, let's do an actual example. We're going to find the value of this particular function on 0 to 3. So here's the function in question. We're going to use our calculator to calculate that. So all of these are going to be pretty simple. You're going to type them in your calculator. What we're going to do by hand is this part, which is just finding out how wide it is. That is 3 wide. So let's write it in the mathematical terms we're looking for. So we're going from 0 to 3 of 4 minus x squared dx. And that's going to be over my average, 3 minus 0. You'll notice the same numbers will come from the integral that will come from that will show up in your denominator. This in my calculator. Let me calculate it. We're going to make sure our calculator is in radian mode the entire time we do any of these, just in case we have to use trig. And we're going to go to math, and we're going to go to 9, which is function integration. We're going to type in 0 to 3. Our function is 4 minus x squared dx. And I hit enter, and I get 3. So this is a calculator. This is handwritten. We get 3 by the calculator and 3 by 3 minus 0. So we're going to say the average area per unit. My dog is barking again. Average area per unit is 1 units squared. All right, so 1 unit squared. Let's see what this is. Let's see what this is truly saying. So average. This is all I expect of you to be able to calculate. Average area per unit is 1 unit squared. I'm going to show you how this comes to be, but again, this is the only thing that I expect of you to be able to calculate. So let me quickly demonstrate why this is what it is. So I'm going to draw in an x and y axis and show you what this function looks like on the graph. Here we're going to throw in some, we'll throw in some numbers like 4, 2, 3, and 1, -1, -2, -3, -4, -5. I'm going to spread this out a little bit. We're going from 0 to 3, and I understand that this is not scaled great, but I want you to see everything that you can possibly see. So I'm going to scale it quite wide on the y-axis. Okay. Let's graph it with an xy, with xy input. So x and y, 0, 1, 2, 3 is where I'm looking. We're going to 0 would give us 4, and then 1 squared is 1, 4 minus 1, 3, 0, and negative 5. 3 squared is 9, 4 minus 9 is negative 5. Okay, so let's graph these. 4, 0, 1, 3, 2, 0, 3, negative 5. I'm going to mirror it on the other side. This is a parabola, so it's good to see kind of what it would look like if it was all drawn out, even though it's not applicable to what we are doing. Okay, not too bad. Remember, our areas of integration are between 0 and 3, so I'm going to draw that in. All right, so 0 to 3 is my area of integration. We are also looking between the curve and the x-axis. So in blue, I'm going to shade the positive area here between the curve and the x-axis. That curve right there could be, if we look at it as a rectangle, 2 by 4 would be a max of 8. However, it's more triangular, even though it's not. So we would be looking at a total area a little bit more than 4. Here in red, I'm going to shade between the curve, the x-axis, and between our intervals of integration. Now, we're not doing this right here. That's not between the curve and the x-axis. We have to be careful that we shade appropriately. If you want to, draw in an ambiguous line right here from 0 to 2, and that will help you break it, the lower and upper limits. Instead of from 0 to 3, we would do it from 0 to 2 of the function that's in the positive quadrant, and then from 2 to 3 in the negative quadrant. It kind of helps you see why we're shading just that area between the x-axis and the curve. And if you need a little bit further, just look at this amount, that right there. That's why we're shading those sections. Okay. I'm going to take those out though. This one again, triangular. From 2 to 3 is 1 unit. Down 5 is 5. So it's about 2.5-ish in terms of negative area. When you put the positive and negative area together, you get this as a result. You get 3. That's what we did when we did it using our calculator. It added positive and negative area together and got 3. What we're trying to look at though is the average per unit. So the only way to average the 3 would be to do this. And I'll use brown here. Not drawn to scale, but 1 by 3, that would be 1 unit, 1 unit. This is 1, 2, 3 unit. Oops, I don't know why I did that. 3 units with a height of 1. So that's your 3 units. That's your average of 1 per unit from 0 to 1, 1 to 2, 1 to 2 to 3, and 1 unit high. That's where the number 3 comes from over the course of 3. That's the only way we would represent it. So that, if you take the blue and the red, mix it together, you get the amount that's in brown there. Okay, so all I'm going to do now is I'm going to do a couple problems, but I'm going to start a new video just so that we don't lose this one. Okay, welcome back. So we're at the example problems now. I'm just going to do a couple just so that you can see how they're a little bit more challenging, but they're definitely easy enough to complete. The first thing I'm going to do is just label the ones. This is just like example number 1 in the notes. these first few slides are just like example number 1. And you can see it's a variety of, just a variety of different problems. Example 1. And this is where example 3 comes in. Remember I said you're not accountable for example 2. And I think this one, average value, again, is example number 3. Okay. So it's just the last 2 slides then that are, or your last page of your notes, which is example 3. All the other practice problems are example 2. So let's do, we just did example 3. So let me go to this one because it looks scarier than what it is. We are going to focus on number 31. Here's an example problem. Here's our function, sine of x, and our lower limit of integration is 0. Our upper limit of integration is pi. We're going to grab this one right from the calculator. And the question is, what is the average? So it's going to be pi minus 0. So let me do this in the calculator. Again, this radian mode is important. So math 9, 0 to pi of sine of x, close parentheses, dx, and we get the number 2. So the amount of area under that curve from 0 to pi is 2. The way to average it would be finding the difference between pi and 0. So 2 over pi is our number we are looking for. This is going to be our answer, 2 over pi. Now, if we can leave it as an exact value, we will. I will show you what the approximate value would be if we are looking 2 divided by pi is about 0.64. Now, I would rather see an exact value if possible. Some of these you won't be able to, and that's fine. But it's about 2 over pi units squared for our the average value. Just like, and so this one you probably won't be able to get that. I can already tell. E to 2e of 1 over x dx. E is in your calculator, it's right below your pi key. We're going to go from 2e so we're doing 2e minus e, which is just 1e. You don't need the 1 there. Let's see what we get in our calculator for that one. We'll get e 2e 1 divided by x dx. Ooh, we get 0.693. It's a decimal that goes on forever. So at this point, you know what? It's fine to then divide by pi. I apologize, divide by e. And you'll get approximately 0.2549. So let's say just 0.25 units squared. So it's about 1/4 of a unit. We should really be saying units squared here. Okay. This one, so that's it for that one. This one, you're going to want to write it as 1 over cosine squared x from 0 to pi over 4, and you'll get pi over 4 minus 0. When you end up doing that, you'll get pi over 4 in a denominator, which actually, whatever number you get up here doesn't really matter. You can actually multiply it by 4 over pi. Don't forget that the reciprocal of pi over 4 is 4 over pi. I'll let you do those on your own, though. Just a little note for that one. Going back, let's do number 5 here, and then I'll let you guys go. We have the area here is 3 if we go from 0 to, whoops, if we go from 0 to 3, we get an area of 3. If we go from 0 to 4, we get an area of 7. These actually overlap. You'll notice that 3 is in between 0 and 4 on a number line. So it's okay to think about this. If we have 0 to 4, whatever area is happening from 0 to 4, and let me just shade a random area. If we take away the area from 0 to 3, let me pick this color. If we take away what's happening from 0 to 3, whoops, then that would leave us with the area from 3 to 4, which is what we're looking for right here. So all you want to do when you set yourself up for success here, you're going to say the integral from 0 to 4 of f of z dz minus the integral from 0 to 3, because those two things are the things you have, f of z dz is equal to the integral from 3 to 4 of f of z dz. If that's what you're looking for, you can now substitute in what you know. You know 0 to 4 has 7. You know that 0 to 3 has 3. So the area then must be, 7 minus 3 is 4. So this is 4. Okay? You're actually allowed to reuse that if you need to. The difference here, you can't reuse it for this because that's f of t. So the reason why they change all these variables is because they don't want you reusing something you already found. Oops, I keep making that mistake. Here, okay. So this z has to do with these z's, and that's fine. But these u's, this t, now we can use for here because they just don't want you reusing this. Because, see, 4 to 3, they don't want you just saying, well, I'm just going to flip it and make this negative 4. They're trying to say that this function's unique, even though you can use these functions to find it. Okay, so you just rotate this, 3 to 4, throw a negative out front, f of t dt, and then you would go on your way and find that one. All right, I'll let you go. Good luck on your exams, and just remember, well, before we go, just remember you have to take your quiz. So let's see, next week goes from the 7th to the 11th. So Monday is 5/7 to Friday 5/11. It doesn't matter what class you're in, but you can come take your quiz during PLT time, off-roll time. You can stay after school, or you can take it in class. I'm giving you guys this many options because some of you will be there most of the days while others of you won't be. It's going to be a mix of who's there. If you have any questions, ask me during class, but these videos will be posted to Google Classroom, and you can watch them as many times as you need to be successful. Okay? We'll probably do the same thing the week after. I'm not sure if I'll be making videos or not, but I'll see you sometime next week. All right. Take care.